Yes, hi. Hi everyone. Good morning. Yeah, so do you guys have any questions in the last session? Anybody have any questions? Yes, guys. I can see only one response. What about other guys? Nobody has any questions. No one has any doubt. All right, then. If you don't have any questions, we'll go to the next part. Yeah. So in the last session, that is 18 Jan, we have discussed the first fundamental blocks of PCA and we have discussed multiple scenarios where we are actually trying to find the importance of PCA and its working, right? Now, here we are interested to go with second fundamental building block of PCA, that is your variance, right? So let us understand that before moving further with the next part, that is PCA in Python, right? So after this, we are going to see PCA in Python, right? After this second fundamental building block. So here we'll learn about the concept of variance and its importance and use in the PCA, right? Concept of basis vectors and how you can use different basis vector to represent the same information. We already have discussed that. By the way, have you guys tried these questions which I have given to you? Anybody tried this? Yes, guys. Did you solve this? Okay, very good. What is your answer, Darshini? What's your answer for this? Let me check. 8131. The first one, no? First one is 8131. Okay. Let me check. 918. ठीक है. First one is, you're talking about this question? Yes, Darshini, your answer for this question I'm asking. Alien one. Okay, alien. Alien question, let me just check. Where is that? Alien, yeah. Okay. First question, where is that? Alien question. This one. Okay. So what have you got? Answer for this one. Representation of the same in alien basis. What is your answer? No, it is wrong. It is -1 and 26. -1 and 26. What you have to do is, see, you have been given this, no? So what you have to do is this 1, 1, -2, 1, inverse of this into 25 and 28. That's what we have to do. We'll get this. And what about second answer? 918. Second is correct. Very good. Second is 918. This is correct, right? 81, 31 is wrong. चलो ठीक है. Very good. Let's go to this now. Let us try to understand the PCA fundamental building blocks, fundamental building blocks of PCA. So we are going to see introduction to variance, variance as information, right? Directions of maximum, variance, and the workings of PCA, right? We are going to understand this. So what is variance basically? Uh, in the previous session, we have learned about first fundamental building blocks, that is your uh, the idea of basis and change of basis. You saw how a simple change of basis led to a dimensionality reduction in the case of roadmap example. And then you also understood how you can represent the same data in multiple bases of vectors, right? However, we did not know how to find those ideal basis vectors and what exact properties they must satisfy. In this session, we'll get to do that by understanding variance as information. So how do you understand variance as an information? Let's try to see that, right? So what do we have with us is we have one diagram that is nothing but okay. So we already have discussed previously, you already have learned certain methods through which you delete columns, right? Methods through which this is through, not thought, method through which you delete the columns or delete columns, right? By checking what? The number of null values, unnecessary information, and in modeling by checking the p-values and vi scores, right? Now, PCA gauges the importance of column by another metric called as variance, right? PCA, what it does, it gauges importance by another metric called as variance, And how varied a column's values are? How varied or varied columns values are, right? So let's go ahead and let's look at some example in the next segment and get an intuitive idea of what variance actually means. So if I give you a black image, simple black image, right? If I just give you simple black image, this one, right? Are you trying to get any information from this image? Do you get any information? Do you guys get any information from this image? Obviously no, right? So my image one is this. Variance as information, like information variance is very less. Where there no any change in the data, right? But if I just give you some colorful image like rainbow with lawn, something like that, the Microsoft uh, photo, right? Suppose if I give you this one or this one, Microsoft desktop image, something like that. So suppose let's take this, or let's take this. So if I give you this image, you're getting some information, like you are understanding something from that information, right? So image, image, if the variance, if the uh, values in the columns varies, or values in the image varies, then you have some information in your data. Then you have some information in the data, right? So as you saw in the example, the first image did not have much information in it. Speaking of it in other ways, the pixels are arranged. It is the same color throughout. Pixels are arranged and it is the same color throughout. However, there are a lot of other things that you could distinguish easily in second image. Therefore, the image has a lot to offer in terms of information. This image has a lot to offer in terms of information. Simple. So the pixels have a lot of variety, and therefore, the image has more variance. Image has more variance. Yes or no? In terms of information, the pixel has a lot of variety, and therefore image has more variance. Pixels has a lot of variety, and therefore that image has more variance. And more variance means equivalently. Can I say more variance means equivalently more information? Can I say this? Yes or no? Yes or no, guys? So more the variance is, more information you can get from that particular data. So let's try to understand this example for variance is equals to information, right? How can I say variance is equals to information? Let's try to understand this. So what I'll do is I'll be actually taking this. Let's increase font. Let's color this to black. Sorry, yeah, and this. Right? Now let us take some example, like we have patient ID, we have height in centimeter, we have weight in kg, and we have age. So we have patient P1, we have patient P2, patient P3, patient P4, patient P5. Height is 165, 155, 165, 160, and 160. Weight is 55, 71, 88, 105, 94. Age is 22, 22, 22, 22, 22. Right? Let's try to understand this now. So for which column is more important for us. Which variable should you drop among this? What do you think? Which variable you should drop among this? Age can be dropped. Very good. Why? Why age can be dropped? Yes, guys. Why you should drop age? As it has less variance. Very good. See, what we'll do now is the column which has less variance are least important for us anyway, right? So that has to be true. So what I'll do is I'll just try to find the variance between this columns out there, right? So the variance for all these columns are sorry is what is your understanding of variance? Is it is nothing but average squared distance of each data points with respect to mean. So we'll find mean first, or we have directly formula, no? Let's use that variance of this. It would be this 17.5, right? Variance. I think variance of entire population variance dot s 14 65 55 65 60 60. It should be 14, I think. But anyway, let's consider. Yeah, it should be 14. Yes. So weight variance is this one 311.4 should be 55 0 90 91. No, okay. If I just do to it 94 94, then the variance P. Or if I just drag this down, can I get the answer? I'm getting the answer. Okay. Now what is your variance for age, guys? What's your variance for age? It is 0. So key takeaway from the above lecture is to measure the importance of a column by checking its variance value, right? To check the importance of a column by checking its variance values. So if a column has more variance, then this column will contain more information. Simple. The geometrical interpretation of variance is like this. Geometric interpretation of variance. So suppose if somebody asks, I don't believe in what you are saying, I have some proof for you guys, right? I have some proof. Like higher the variance, higher is the information. How can you see that? See, what I'll do is I'll draw a diagram. On x-axis, I will be having, let's say, height, right? And y-axis, I have weight, right? As weight variance is high, so I'll just try to, plot a scatter plot between those two. Let's plot the scatter plot. Insert, chart. This is your scatter plot, right? This is your scatter plot. But is it correct? Height in centimeter. 160, 164. Okay. Okay. But in our case, our variance for weight is high or height is high? Height. Weight is high, no? Weight. Anyway, let me draw one figure to understand this. Sorry. Let me draw this. Let me just remove this. Let us draw one figure. Let's say whatever we have seen was correct. I think let's go with that. This is height and this is weight in kg. Suppose weights data points are like this. 1, 2, 3, 4, and 5. Right? So the variance, if you just draw it, extend it to the axis, which is this one, the variance for height, it varies from this place to this place. Right? This place to this place. So this much is your variance for height. But in other words, what is your variance for weight? Weight varies from this position to this position, let's say. Here also we have one, suppose. So your variance for weight is this. And which value is high? Variance for weight is high or variance for height is high? Length. Which one is high? Yes, guys. Height is less, weight is high. Right? So weight is more important than height. Why? Because it has a lot of spread we can consider, no? Variance as information. It gives you more information about that column. So the red line or the black line in this case, black line on height and weight axis are shows the spread of the projections of the vectors on those axes. Black line shows the spread of the projections of the vectors on those axes. And as you can see here, the spread of the line is quite good on the weight axis, weight axis as compared to height axis. Right? Hence, you can say that weight has more variance than height. Weight has more variance than height. Yes or no? The idea of the spread is the data being equivalent to the variance. It's quite an elegant way to distinguish the importance of direction or important directions from the non-important one. So I can say weight is important for me as compared to height, right? So likewise, you can plot your data and you can find understanding of which column is important, right? Now, let's go with the another topic, that is directions of maximum variance, right? You have understood the basis and change of basis. Let's try to relate it over here, right? Do you remember we have found the basis vector in the last session, the geometrical representation? Do you remember that? Change of basis geometrical distribution. Can you remember that? Suppose this is your original axis, right? We are shifting this axis to like this, right? This one, this one. Yes or no? Is it clear now for you, everyone? Is this thing clear to you? Yeah. So that's what we have. Like we are just finding the change of basis and we are just finding the directions of maximum variance. What is directions of maximum variance? See now, if you just project it like this, the variance is this much only, right? But if I just change the direction, change the basis to this vector, to this one, my change of basis, my direction or my variance is increasing from this to this. So which one is high? This one is high or this one is high. Obviously, the hypotenuse will always be high, right? So this is high, no? And this is why we are finding the basis, right? This is why we are finding basis vectors. Why? Because in basis vector, we get the direction. Direction of what? Direction of maximum variance. And that is what the idea is, right? Here on x and y axis, we are not getting the maximum variance. Suppose on y axis, this is your variance. On x axis, this is your variance. So we have two columns. No, we want to reduce column. So idea here is to find basis vector. We'll get maximum direction of maximum variance, and another direction will be obviously zero. Another direction will be obviously zero. So that's what the idea is, to find the directions of maximum variance. So you saw that when variance are unequally distributed among the original features or columns, that is, some columns have much less variance, some column have much less variance than others, and it is easier to remove those columns and do the dimensionality reduction. But what will happen? What about the scenario when the variances are pretty similar? What about the scenario where the variants are pretty similar? For an example, take a look at the following image containing the height, or I'll just draw this height and weight information. So if I have some data where I am having uh, information about weight and height, but that data is quite, both has same variance. Can happen, no? This one, this one, this one, and this one. So the variance will be from this to this, suppose. So my variance is this much, right? Here also, my variance is from this to. Now it looks high. It looks high. What if I just remove this, right? What if I just remove this? And if I just add it to, let's say, here, right? So it will be from this to this, right? So my idea is to show you, what if we have both the variants are same? What if we have both the variants are same? Can you tell me which column is important? Here we have weight, here we have height. Can you tell me? Obviously no, right? We cannot tell. We cannot judge which column is important. So what should we do for this? Then we should find the basis that we have already seen. Maximum variance, the direction of maximum variance. So that's why we are finding, or we were trying to find uh, basis vectors, right? So after going through this session, you have more or less understood what PCA does. It changes the basis vector in such a way that what PCA does is it change the basis vectors in such a way that the new basis vectors capture the maximum variance or information, and in the next part we'll get to know how this happen easily. You already have got an idea about this, how this happen easily, but let's see this, right? Already we have discussed, we are finding the change of basis vectors, and we are getting direction of maximum variance, yes or no? So suppose, not this one, this is also same. Okay, okay, let me just draw then, or let me just check here, direction of maximum variance. Do we have any diagram for this? Right, Do we have any diagram for this? Just give me a minute, guys. Just a minute. Just give me a minute. Let me take one figure. Meanwhile, you revise whatever we have discussed till now. This is what I was talking about. Uh, yeah. Just a minute. Huh? Just give me 2-3 minutes. The directions of maximum variance we want. No? Can I get a figure for this? Yeah. Hmm. Just a minute, guys. Let's. I am. Just a minute. Yes, so we have this figure, right? We have, we can take any figure from the net, a little possible. Okay, let me take the correct one only. PCA, variance as information or maximum. Yeah, this is what we are talking about. Yes. So let's take this. I'll just share my screen. Share my screen. Yeah. Right. The directions of maximum variance is this. So the principal components can be visually represented as shown in the image, this image below. Also, one principal components are found out. PC assigns the percentage age variance to each principal component. Essentially, it's fraction of the total variance of the dataset explained by a particular principal component. Now, what is principal component, guys? Nothing but the direction of vector, or basically the vector which gives first maximum information of the data. Yes or no? So my PC1 is vector which gives first maximum information about the data. PC2 is vector which gives second maximum information of the data. Similarly, you can have PC3 depending upon the columns in your data that you have, PC4, PC5, PC6, like that. Yes or no? So it's kind of difficult to visualize this properly, but let us try to understand this by using this uh, visualization tool. So there is one more thing which is known as Sitosa IO. Yeah, this one, where you can get to see PCA, how, I mean, the visualization part of the PCA, right? So this is the original data set. What you have done is you have converted this into uh, this principal component, the maximum variance. What is that? It is this one. So let me just take, this is what we have taken, right? This one. And then we have converted this to, we call this as principal components. We call this as principal components. So my principal component one has maximum information, 100% information. And principal component two, that is this vertical direction, this one has very less information, right? And I can drop that column, PC2. Similarly, 3D, what happens is, suppose you have this is your data, right? You can imagine this is your data, right? On this axis, can you see this? This is your data set. So you kind of trying to find the principal component which gives you the maximum information, PC1. Let's try to understand this. I think this is my maximum information. This one. I think this one, right? PC2 is this. So likewise, you have to do. I mean, your model will perform this thing. You don't need to worry about this. If you just move your cursor and if you just move to the different orientation, you can see that your principal component information is also varying. And you can just try to understand this explanation, like what if your data has way more than 3 dimensions, like 17 dimensions. So in the table below is the average consumptions of 17 types of foods in grams per person per week for every country in UK. So this table shows some interesting variations across different food types, but overall differences aren't so notable, right? Can you just visualize from this which is least important? So we use PCA for that, right? So you can just have a look at this. I'll just share this visualization here. Just study that. So also one of the principal components, once the principal components are found, PCA assigns what it assigns? It assigns percentage variance to each principal component. For example, what is percentage variance? It is essentially the factor, it is essentially the fraction of the total variance of the data set, which is explained by particular principal component. So if you have more than, let's say if you have 11, 12, or let's say 13 columns, 13 variables, at that time your principal component one, it is not possible to give 100% information by this principal component one itself. Can you just imagine you have 13 dimensions like that? Our human eye is very difficult. It is very difficult for us to visualize 13 dimensions, right? That's why PCA is there. So PCA does your task. So original data set, what happens is, suppose you have this point X and Y. This is P1, this is P2, this is P3, this is P4, this is P5. This is going to be P6. This is going to be variance, right? Suppose this is your data 3, 2, 3, 4, 6, 7, 8, and is equals to variance P is going to be 4.667. Y is 1, 1.5, 2, 3, 3.5, 4. Variance dot P is going to be 1.16, right? And the percentage variance or information is percentage of variance or information is going to be is going to be yeah, it is going to be yeah, it is going to be if you just want to try this, it is 4.67 divided by 4.667, whatever it may be, divided by total variance, that is 4.67 plus 1.16 or 167, right? It is, and if you just do is equals to, so your first column, that is X, itself gives you what? It gives you what? It gives you the 80% information about the data, 79.9, and remaining 20% will be given by this. So which is your important column? This one. It gives me the 80% information about the data. Now what I'll do is I'll just try to modify this. I'll apply change of basis, and I'm going to find the direction of uh, direction of maximum variance. Direction of maximum variance. So PC2 is this, and this is going to be P1. Same. So I can copy this from this point to this point here, here, right? New will be, let's say 2.24. 3.35, 4.47, 6.71, 7.83, 8.94, 5.83. Simple. My y new is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Because this is my maximum direction, right? Now the variance dot p for this is going to be 5 point, what is it? Sorry, variance is 5.83. I already have calculated. Variance dot p for this point is 5.83, and percentage variance is going to be 100%. Yes or no? Is equals to 5.83 divided by 5.83 plus 0, right? Simple. Are you guys getting this? So 100% information here, 0% information here. If you do what? PCA. And that's what the whole idea is. Now, is this thing clear to you, everyone? Anybody have any questions?
Yes, clear.
So since the 100% of the total variance of or information of the entire data set is present in only one of the columns, that is PC1. We try to convert into principal components, right? So we can safely drop my another column, that is PC2, PC2, and still be assured of what? Losing no information in my data. Isn't it simple? So that's what we have. We'll take a short break of 10 minutes. We'll be back in just 10 minutes. We'll back break. Will be we actually have to see Python, PC in Python, and somewhat what we can say workings of PC is remaining for us. So working of PC will do, and I'll summarize this for you. Then we are good to go with the Python part, coding part. All right. So now the last part, workings of PCA. We'll see that. So until now, let me write down it first. Workings of PCA. So until now, you have learned the two building blocks of PCA, that is basis and variance. Now, in the following video, we'll make use of both the terms to make you understand the objective that PCA aims to achieve for, right? Not video. What is this? In the following session, we'll make use of both the terms to make you understand the objective of PCA, what it aims to achieve, right? So, what is PCA, guys? Uh, let us summarize the steps of PCA. What we do is summarizes the steps of PCA. But first, we find n new features, right? We choose a different set of n basis vectors, non-standard, and these basis vectors are essentially the directions of maximum variance and are called as principal components. So what we do is we choose a different set of n basis vectors that is non-standard, and this basis vectors are essentially the directions of maximum variance and are called principal components, right? Then what do? We express the original data set using this new features. So we transform the data set from the original basis to this PCA basis. And then we perform dimensionality reduction. That is, we choose only a certain k where k is less than n number of the PCs to represent the data, right? And we remove those PCs which have fewer variance. That is, we explain. Oh, just a minute. We explain that is fewer variance means which explain less information, right, than others, right? Then this is what we have for the entire PCA. Then what happens is, what is PCA? It's a it acts as a pre-processing tool in the ML pipeline. PCA acts as a pre-processing tool in the ML pipeline, predominantly used for dimensionality reduction to improve model performance, right? And the approach is as follows. You have variable 1 here, you have variable 2, suppose, variable 3, variable 4, and you have PC underscore 1, PC underscore 2, PC underscore 3, PC underscore 4, and you have 85% variation. You have 7% variation. Sorry, first of all, I should write down this. No, we have 20% variation. This is 30% variation. Suppose this gives 27% variation, and remaining 23% variation is given by principal component, sorry, variable 4. Now we convert that into principal component, right? Convert that into principal component. And this is how it looks like. As you can see over here, principal component 3 is 5% variation. Principal component 4 is 3% variation. Right? Now, note, just write down this note, just add this note. The number of principal components is the same as the number of columns in the dataset. That is, PCs are sorted in descending order of information content, right? So number of principal components is the same of as the same number of columns in the dataset, and pieces are sorted in descending order of the information. Like principal component gives us the 85% information, that is variation, then 7, then 5, right? That's what we have. And now before we end this session, we have seen the we have done good amount of practice on change of basis and eigenvalues and that kind of thing. Let's not discuss that. So what is PCA's role? PC's role, guys. PCA role. What is PCA's role? What is PCA role? In ML pipeline is almost solely exist as a dimensionality reduction tool. Basically, you choose a fixed number of PCs that explain a certain threshold of variance that you have chosen, and then use only that many columns to represent the original dataset. So what happens is we'll set a threshold, like we want only 90% of the information. So that I'm going to get by only this two principal component, right? So if I add PC1, I mean if I only consider PC and PC2, these two columns, I'm getting 85% plus 7%, that is 92% of the information of the data. Yes or no? So I am getting 92% of the information. I am satisfied with that. I don't want 100% of the information. I don't want these four columns in my data set. I want to remove those. So that is what we happen. That is what we set a threshold. We set a threshold as 90%, let's say. So let's say you have 20 columns, right? You have done the principal component analysis, and only by using 5 principal components, first 5, you are getting 90%. It is crossing this threshold. So you're satisfied with that. You'll go with the 5 columns only. That's how the columns will be removed. Yes or no, guys? Is this thing clear to you? Anybody have any questions till now? If it is clear, let's go to next part. That is PCA, applying PCA in Python, right? So let's work on two dataset now. Anyway, if time is not sufficient, we'll just be having a good amount of practice for PCA itself. right? Let's go with this now. Let us go with this only. Then we see what can be done. Yeah. So what I'll do is on your drive, let me create A31. Today is 19th Jan 2025. PC Python, right? Anyway, have you guys submitted this or no? Gopi has submitted. Okay. So let me just take data set. Let me take one data set here. Users here. Next. See. This is what we have. Okay. And let me just uh, take create Google Colab. Let us create Colab. Let's do this. Create and share. Let us do this. Okay. So PCA on Facebook data, right? So just a basic level of project we are going to do over here for PCA, and then we'll see some advanced part if time permits. So I'll just upload this data which I'm going to use. And I'm going to import necessary libraries, import necessary libraries, import pandas as PD, import numpy as np, matplot v dot pyplot as plt from sklearn dot preprocessing, import label encoder from a robust scalar, from a scalar dot model underscore selection, import PC. Cannot import PCA. Why? Sorry, decomposition, not from sklearn dot decomposition. If you just don't know, uh, don't have any idea about the package, you can directly write down PCA sklearn pack. We'll go to official documentation or scikit-learn. Decomposition spelling is wrong. And you can copy from this position, right? Simple. Right. So I'll write on df is equals to pd.read underscore csv, and I'll just copy path. I'll run div.head. Sorry, this is not run time. It's not run. And then I'll write on div.info. This is what I have over here. Right. Then I'm going to drop null values permanently. If I have null values, it will not be there. Right. Now, let's do encoding, because for some of the columns uh, they are this categorical. This type column is categorical. So let's apply this label encoding for that. So I'll write an ali is equals to label encoder open close bracket df of type is equals to ali dot fit underscore transform, and df of type is what I'm expecting over here, right? Then rs is equals to robust scalar open and close bracket rs dot fit underscore transform on df, and then I'll write down scaled underscore df is equals to pd dot data frame data is equals to rs dot fit underscore transform df comma columns is equals to df dot columns. Simple. And then I'm going to take scaled underscore df dot head here, right? Then I will take PCA and I'll start doing on this PC. So if you just see, earlier data was not scaled earlier, right? 13994. This page total likes are in 6 digit. This category 2 digit, 1 digit, 2 digit, 4 digit. So it has to be in single range, right? So we'll do that by using scaling. And once the data is scaled, all the data are converted from 0 to 1. Simple. So what I'm going to do is I'm going to create a custom function, custom underscore PCA. That I'm going to pass x n underscore component is equals to length of x dot columns. Then for I in range of what? 1 comma n underscore component. Small PCA is equals to capital PCA n underscore components is equals to I p underscore component is equals to PCA dot fit underscore transform capital X. EVR is equals to NP dot cumulative sum PCA dot explained underscore variance underscore ratio underscore, and if EVR of I minus 1 is greater than 0.9, PCS is equals to I. I'm going to break this, right? And then I'm going to print this, what? Explained variance ratio after PCA is EVR, and I'm going to creating a data frame, principal components. I'll explain this. What we are doing over here is column is equals to blank list for j in range 1 comma PCS plus 1 column dot append this string PC underscore plus str of j and PC underscore df is equals to pd dot data frame p underscore component comma columns is equals to call and return PC underscore df. Right now, what we are going to do, what we are doing over here is, see, as I told, we set the threshold as 90%, right? So here we are setting threshold as 90%. What is this explained variance ratio, guys? It's nothing but same thing over here. This is known as explained variance ratio. So we are taking cumulative sum of that because we are interested to find this sum, right? 85 plus 7 is certainly greater than 92. So we are just taking cumulative sum. Do you guys know cumulative sum? Or if you don't know, you can tell me, I'll explain that. Do you know cumulative sum, everyone? Do you know this? It's simply in our school level, we used to do this, right? Do you remember that? So we used to take cumulative sum 85, 85 plus 5, 90, 90 plus 6 is 96. And let's say this is 4. So 96 plus 4 is 100. So this column is known as cumulative sum, right? Cumulative sum, right? So that is what we are doing over here. Now I am creating a function in that I am going to pass only x. What is that x? The data frame basically. And n underscore component is equals to length of that x dot columns. So whatever columns do we have, whatever data frame do you have, suppose in this data frame, how many columns do we have? We already have discussed, right? It is 18 columns. So length of x dot columns will be going to be 18. Simple. Length of x dot columns is going to be 18. Then for I in range 1 comma n underscore components, for I in range 1 comma n underscore components, for I in range 1 comma n underscore components. It means suppose you have 20 columns, right? You have to pass through all the columns out there. So you should write down which range for I in range of, for 20 columns, you should write 21, right? Right? Yes or no, guys? If I just write down for I in range 20, and then if I write down print I, I'm not going to get 20, right? Will I get 20? No. So if I, in order to get 20, in order to want 20, you should write 20 plus 1, that is 21. I in range 21, or I in range 21, right? Is this thing clear now, everyone? This part? Okay, so that's what we are doing in 1 comma n underscore components plus 1. Here also we are doing plus 1, right? So PCA is equals to PCA comma n underscore components is equals to I, and P underscore component is equals to PCA dot fit underscore transform on X. By using this line, we are just creating an object. First of all, small PCA is equals to the package, PCA package. In that, we are going to pass in underscore components is equals to I. So 1 by 1, 1, 2, 3, up to 20, it will pass, right? And then fit transform will transform, do the PCA, right? Fit transform will, what it will do? It will fit and it will also transform. So both the thing simultaneously it will do. Yes or no? So if I just do fit transform, I'm getting basis vectors and that kind of stuff. I'm getting principal components, and we are defining another object, that is EVR, which is nothing but NP dot cumulative sum of what? PCA dot explained variance ratio. What is explained variance ratio, guys? This is your explained variance ratio. So we are taking cumulative sum of that explained variance ratio, EVR. So that's how this will take place, right? And the moment we achieve 90% threshold, we'll stop it over there only, right? So here, if EVR of I minus 1 is greater than 0.9, if it is greater than 90%, PCS is equals to I, and we are going to break that loop. PCS is equals to I, and we are going to break that loop. Simple. So then we'll print explained variance ratio after PCA is EVR, creating a data frame of principal components. Column is equals to blank list. For j in range 1 comma PCS plus 1, column dot append PC underscore plus string j. So we are creating a blank list column. We are passing this PCS. What is that PCS? It is nothing but principal components, which we have got after setting threshold as 0.9. So suppose out of this 18 columns, 1, 2, 3, 4, 5, or 6. By using 6 column itself, we are achieving this threshold of 90%. So PCS will be what? 6, right? 6 means ideally it should be yeah, 6 only. PCS will be 6. Then it will break, and then we are creating a list of column as principal components. As principal component, passing a loop as 1 comma PCS plus 1, means suppose we are getting 6 principal components, we'll pass a loop as range of 1 comma 7. 6 plus 1 is 7, 1 comma 7. And then I'm going to append this principal component in a string out there, right? And PC underscore df is equals to pd dot data frame, p underscore components, comma columns is equals to call, and then we'll return this PC df. That's what we are going to do. So we are going to create a data frame that is PC underscore df in that principal components, and its column will be there. So if I just write down PC underscore df is equals to, I'll pass this custom PCA function which we have created, custom PCA. And in order to call this function, what we need to pass? We need to pass a data frame. So scale underscore df is something which will pass, because if you don't do scaling, your accuracy will be less, right? So you have to have scaled data frame. You have to pass scaled data frame in that. Now what does it says? This is what we have written, right? Explained variance ratio. So ratio is after PCA is this. So 1, 2, 3, 4. If you only select 4 principal component, your task is done, right? You are getting 92% of the information. So why we should consider 18 columns, right? We should consider only 4 columns. Yes or no? And then we are able to extract 90% of the information from the first 4 PCs, which we have reduced the feature count, through which we have this. We are able to extract 90% information from the first 4 principal component, through which we have reduced the feature count by 78%. How 78%? You just try it. Earlier we had 18 columns. Now we are reducing it to 4. So reduction is 4 divided by 18. So it should be 14 by 18. It should be 77. So reduction is what? Reduction is 4. Or 14 is the reduction, right? Sorry. So we are able to reduce 78% feature count from the data, right? Now, if you have any questions in this, you can ask. If you don't have, we'll go to next part. Anybody has any question? Till now, whatever is being discussed in this, do you have any questions? Just a minute. Yeah. Do you have any questions, guys? Just a minute. Let me just have a look at the another data set we have. Welcome to this mod. So we can have the same data set only, nothing special in that. Special in that. Scree bots. Yes, yes, yes. There's one more thing that I wanted to discuss. Okay, let's go with this. This will be a good idea for you guys. What I'll do is I'll upload this data set on your drive. We have to see another part in subtopic in your PCA domain. We'll see that and then we'll stop here for the day. So in this folder, day 31 itself, I'll create another folder. Let's say 2. And here I'm going to upload that. Yeah. Okay. Let me upload that. Let's upload these two files which we have, right? Yeah. Now I'll just share my screen. I'll just share my screen. So here we'll create new collab notebook, right? And let's create a share. ठीक. Let me upload that file first of all. Let us go PCA. Let's say PCA demo, right? So PCA demonstration in Python, right? Importing necessary libraries as import numpy as np, import pandas as pd, data is equals to pd.read underscore csv, iris dot csv, right? And now we'll write on data.head, open and close bracket. So sepal length, sepal width, petal length, petal width, and iris. This is your data, right? Now, if I just write down data.describe, I'll explain what this data is all about. So it's very common data set already available and used for study purpose. We have one flower, iris flower, this one, right? So ideally, not ideally, we have sepal and petal, right? These are the terminologies associated with flower, right? So if you just search sepal and petal, so you'll get an idea about sepal and what is sepal, what is petal, right? So this is known as sepal. This is known as sepal, and this small leaf you can say is known as petal, right? So we have sepal length, petal length, sepal width, petal width, right? We have sepal length, sepal width, petal length, petal width. So this data set is all about that, right? This data set is all about that. So I'll just copy this figure, paste it over here so that you can get an idea about that, right? Now, uh, we what we'll do is what we have to do is another thing is there are three species of iris. We have versicolor, setosa, and virginica. We have three species. What is that? Versicolor, Setosa, and Virginica. So we'll just try to take it all. Versicolor, Setosa, and Virginica, right? So depending upon the data, depending upon the sepal length, sepal width, petal width, we have already collected data set, which is if sepal length is 5.1, width is 3.5, this is 1.4, petal width is 0.2. So your iris flower is Setosa. And we still have, I mean, here we are not getting to, we are not get to see uh, different uh, what we can say species, but we have that data set. If you just take value counts, you just take value counts, you'll get an idea about, it should be data, right? Not df, should be data. You get an idea about what? An idea about what? Setosa, versicolor, virginica. Yes or no? Like we have 50-50-50. So 150 data points are there and count is 50-50-50. Simple, right? So from what we'll do is we'll apply PCA on the data that we have. From sklearn dot decomposition, we're going to import PCA, and question mark PCA is like, if you just write down question mark PCA, you'll get a help related to PCA, like what are the different parameters that you can pass, what are the different arguments that we have, right? Or everything related to PCA is explanation and what is that. So you can write down that. Anyway, I'll just comment this thing and let's move to the next part. So small PCA will be equals to capital PCA random underscore state is equals to 42. Then PCA, small PCA dot fit. I'll fit it on X, small x, sorry, small x. Because we have created small x, no? It's not created. Is it not created from my side? Okay, just a minute. After data.describe, after data.describe, let us define y. So y is your target variable, right? All every time what is your target variable? Y. Here, your target variable is iris. This column, iris column. So that is going to be your target variable. Simple. This is going to be your target variable. This is going to be your target variable, right? Now, see over here. Now, we will kind of put data into X and Y, right? So Y is there. X, capital X is data dot copy. So if you check what is there in X, if you check what is there in X, so this is your X, right? And Y is this. If you check what is there in Y, we'll get this. Simple, right? This, If you just check what is in Y, it says does not have data does not has iris column. So instead of using pop, I'll directly write down data of iris. No, that will be also another method. Okay, we can do this. Then we'll do scaling, because if you just see, it's not there. How it's possible? Let me just restart and run all this. Now what I'll do is, first of all, uh, here, do you think do we have requirement for scaling? Yes or no, guys? This is 2 digit, 1 digit, 1 digit, but all the columns are not in a single range, right? So we'll do the scaling of the data. So I'll write down scaling the data, and I'll write down from scalar dot pre-processing. I'm going to import standard scalar, right? And I'll create an object. Scalar is equals to the package standard scalar. Open and close bracket. And x is equals to small x is equals to scalar dot fit underscore transform on capital X over there. So if you just find could not convert string into this. Okay. Okay. So I should write down here, I should write down capital X is equals to data dot copy first. Right? Right? Yeah. And let's check what is there in X. We are trying to remove the string column, but it is not removed because we are not doing pop method. No, we'll drop this first. Okay, let me just drop which column? Iris column from axis is equals to 1. Right, we'll drop this, and then we are going to write down small x is equals to scalar dot fit underscore transform on capital X. After doing this, if you just check small x dot head, if you just check small x dot head, small x dot head, or small x, if you just check anyway, let us check small x. So it will be scaled data, right? It will be scaled data. Now we can fit this scaled data on PCA over here. This is what we'll do. Right? And if you write down PCA dot components underscore, if you just write down this, you are going to mm, you'll write on PC dot explained variance ratio underscore. So these are the principal components, PCs, right? This is PC1, this is PC2, PC3, PC4. So four principal components are there, right? First principal component itself gives you 72% of the information. Second gives you 23%. Third gives you 3%. Then you are going to import matplotlib.pyplot as PLT. Import matplotlib.pyplot as PLT. And then we'll write on plt.bar. Bar graph will do, explained variance ratio. Like if you select first principal component, right? If you select first principal component, then what will be your explained variance ratio? This is your bar graph. And then you have variable cumulative is equals to np dot cumulative sum pca dot explained variance ratio underscore. Now, basically, if you select first principal component, you get 77, 72, right? Second principal gives you only 23%. So like that, you can get an understanding of which principal component you should select. Now, you learned how to perform PC on your dataset and obtain principal components. The final PCs that you got were as follows. Yes or no? So we'll try to understand one important concept over here, that is Scree plots. Let us try to see that. Scree plots. Excuse me. All right. So I'll just write down over here. I'll just write down over here. Scree plots. Right. What is Scree plots? So PC1 is given by the direction 0.52. And whatever it may be, like you can get this, right? Just a minute. Let me take this. Right. PC1 is given by the direction this, and so on. The principal components of the same number as that of the original variables with each principal components. Yes or no? Original variables, like principal components are 4, original variables are also 4, right? This information, the component, uh, this information would enable us to know which principal component to keep and which to discard to perform dimensionality reduction, right? Now let us understand it further in the following part about the Scree plots. What do you mean by the Scree plots? So I think we have already given this heading. Let us try to understand what is this Scree plots is all about. So first thing, what do we do is, uh, first thing is this first principal component gives me 73%, second gives me 23%, third gives me 3.6%, four gives me 0.5%, right? So as you can see, first principal component, that is this this one, this principal component, explains the maximum information in the dataset, followed by PC2, then PC3. In general, when you perform PCA, all the principal components are formed in the decreasing order of the information that they explain, right? Therefore, first principal component will always explain highest variance, followed by second principal component, and so on, right? This order helps us in our dimensionality reduction exercise, as now we know which directions are important than others. Now in our dataset, we had only 4 columns and equivalently 4 principal components. Therefore, it was easy to visualize the amount of variance explained by them, right? Using a simple bar plot, this one, using a simple bar plot. Then we are able to make a call as how much variance to keep in our data. For example, using the table above, this one, this one. Let me take a table. Let me create a table. Principal component and variance explained by them. This is PC1, PC2, PC3, and PC4. Variance explained is 72.8. This is 23. This is 3.6, and this is 0.5. Right? Let me take this over here. This is my principal component. Right? So as you can see, first principal component, that is this one. Let me write down that here, 0.52 minus 0.26, 0.58, 0.56. This is what we have. It explains the maximum information, the data set. Yes or no? So I can say, if I set 95% threshold, so that I'm going to get it by this first 3 principal component. Or I only need 2, right? 2 principal component. Only need 2 PCs to get 95% information of the data. Yes or no? You try this out. 72.8. 72.8 plus 23%. That is 95.8%. But what happens when there are hundreds of columns? Using the above process would be time consuming. Process would be, I can say, cumbersome, right? Since you need to look at all the PCs, since you need at all the PC, and you would need to, or basically, and keep adding their variances up to find the total variance captured. Yes or no? So instead of that, we use Scree plot. That's why the Scree plots are introduced. Scree plots. What is that? We'll just try to see that. So an elegant solution here would be simply add a plot of cumulative variance explained chart. Cumulative variance explained chart. So what we'll do is, this table is, we already have this table. We'll just take it. We'll paste it over here. We'll add cumulative sum. This will be 72.8. This will be this plus this, and this will be this plus this, right? It should be plus, right? Plus, and this should be this plus this. So 99.9, whatever it may be. So for example, cumulative variance explained by the top two principal components is the sum of their individual variances. Is the sum of their individual variances. That is given by 72.8 plus 23, this one, right? If you plot the number of components on the x-axis and the total variance explained on the y-axis, right? The resultant plot is also known as Scree plot, right? So what you can do is, now I think we'll not get a line chart on this. Right. Line chart is something which we, let's see, line chart online creator, line graph maker. Okay. Horizontal axis are 1. What is this? Minimum, maximum. I don't want this. X-axis label is number of components. Y-axis label is explained variance. Graph name is Scree plot. Y-axis scale is linear. Data labels, enter labels separated by commas. So 1.0, 1.5, 1, 2.0, 2.5, 3.0, 3.5, and 4.0, right? Data values. My values are cumulative variance, this values. 72.8, comma, 95.8, comma, 99.4, comma, 99.9, right? And if I just, this is my Scree plot, right? 0, 0 is remaining. Let's go with 0. 0.0, 0.5. Now, why is it not changing? It starts from, no, start y-axis from 0. That should be turned off. Yeah. And this should be 1. Okay. Now I get it. This should be 1. Perfect. So this is what we have, right? This is known as Scree plots, guys. This plot is known as Scree plots. This plot is known as Scree plot. Am I not audible, guys?
Fine.
Yeah. Just a minute. Yeah, I can see. Am I not audible? You're audible. Can you guys confirm?
Yes, you're audible, Vipul.
Just confirm in the chat. I think somebody has some, so that they will get, like, he will get an idea ki you guys can hear me. Just write down in the chat. Okay, perfect. So this is known as Scree plot. Now this is better representation. Uh, it is a better representation of variance and the number of components needed to explain that much variance. Yes or no? It's a better representation of variance and the number of components needed to explain that much variance. Yes or no? So that's what we have for the this. Now I'll give you one question on this. In this following Scree plot, which you can see, how much total information is written using only three principal component? Using only three principal component. Yes, guys. Using only three principal component, how much information is retained? What do you think? Actually, ideally, this should be correct because we were taking it there. Yeah, this is not correct. This is correct, right? Now, if I just select three principal components, how much information I'm going to get? Somewhere around 99.9, 99.4, right? That's what the question was. Okay. So let's go with the dimensionality reduction now after doing Scree plot. So what I'm going to do is I'm only going to take two principal components, because if I take two principal components, I'm going to get 95.8% information. Yes or no? So why should I go with other principal component? I'll simply write down PC2, or I'll write down PCA with two components. So I'll write down PC2 is equals to capital PCA in underscore components is equals to 2, random underscore state is equals to 42, right? And my new data is going to be PC2 dot fit underscore transform small x, and new data dot shape is going to be 150 comma 2, right? So only two columns we are going to consider. Only two columns we are going to consider. And now we'll see what happens. So new data, my data frame df is equals to pd dot data frame. F is capital, right? Pd dot data frame. In that new data and columns is equals to PC1, sorry, PC1, comma PC2, and I'm going to write on df dot head. Head, right? Then my df underscore final would be pd dot concat what df comma y. comma axis is equals to 1. So I have PC1, PC2, and my iris data frame. And now I'm going to visualize this. This has to be in square bracket actually. Concat should be round bracket because concat is a function. So it has to be round bracket. X is equals to 1 should be round bracket. Right. And if you just check df underscore final dot head, you are going to get this. And I'm going to plot the data now. I'll write on plotting the data. What is that? And if I just write on import cborn as sns dot pair plot data is equals to df underscore final x underscore variables is equals to pc1 comma y underscore variables is equals to pc2, right? And hu is equals to iris comma size of the dots that I want is this. Anybody have any questions now till this point? This is how I can reduce the dimensionality. So I'll just write down heading as dimensionality reduction. Yes. Now, one more thing is remaining for us that we'll do it in the next session. What we can do is we already have checked the we have already have fitted different models, right? Suppose what we'll do is we'll fit logistic regression. I'll just walk you through, kind of give a walkthrough, and then to improve model performance, we'll use PCA in that, right? So what happens is if you have multicollinearity, if you have high number of variables which are redundant, we can use PCA in after performing different models, after creating different models. So in logistic regression model itself, I'm going to use PCA to just improve the model performance. So model without PCA, we'll compare that with the model with PCA. Model without PCA, we're going to compare the performance of model without PCA, that is logistic regression model without PCA. We'll compare this with logistic regression model with PCA, right? So suppose here we have 85%. Here definitely we are going to have increased accuracy, that is 90%. So that's why we PCA do. We use PCA to increase the accuracy as well. To increase the accuracy, right? Is this thing clear to you, everyone? If you have any questions, you can ask. We'll stop here for the day. Otherwise, if you don't have, we'll stop here for the day. Do you guys have any doubts, any questions, anything? Yes, guys. Do you have any questions? से पैसा मिलेगा एफिलिएट इनकम से पैसा So let me have a look at your syllabus. Let's discuss that. Just give me a minute. What is remaining for us till now? Yeah. So we have finished this one, right? Module 9 is finished. We still have this module 10, deep learning. Okay, apply deep learning with PyTorch. This is what we have. Then module 14, 15, 16, 17, 18. Perfect. All right. So today was our 32nd, I think, 32nd session, right? We still have, I just have talked with them. We still can have 22 more sessions, 22, 25 more sessions. So we can definitely finish this within that stipulated amount of time. So don't worry. We still have good amount of time left with us. All right, then if you don't have any questions, we'll stop here. Thank you. Happy learning and revise this. Yes, XGBoost will see, don't worry. It's very simple model. XGBoost. We'll see that.